now and then we're going to describe what you're doing in your experiment. In fact, we're probably going to concentrate on that description on Wednesday. So today we're going to gather the data, do a little bit of calculations if you wish to do those calculations, and then we'll have a nice lecture trying to understand what was happening on Wednesday. The lab write-up can then be completed between Wednesday and the following Monday, which is, what's the date? I don't know the date today. Today's the 9th, so that would be the 16th, I guess. And that's our principal goal for today. So let me start by this quick description of gravity and photons, just to finish that topic, and then we'll move on to today's lab exercise, so it won't take long. All right, well, what I want to talk about is, since we're beginning to realize that photons exist, they are the so-called massless particles, meaning that they do not have rest mass. But since they seem to carry momentum, and that's what the photoelectric effect shows, is that photons carry momentum, that is a mass-like property. So these so-called massless particles do seem to have a mass property to them, at least when they impact things. So now what I would like to do is I'd like to imagine a photon climbing away from a star. Let's imagine that a star produces some light, a photon is produced, and it's on its way, perhaps to us, for us to measure. Since the photon has mass-like characteristics when it exists, that means that gravity should have an influence on it. Remember Einstein's postulates for general relativity. One of the things is that there is no difference between gravity and an acceleration. Gravity should have effect on photons. And that's because at the speed of light, photons seem to have some sort of mass characteristic to them. So all of these things combined together, let's imagine that a photon is leaving a star. Now you can understand why. If a star has a very strong gravitational field, the photon leaves the star and is headed towards you, it's going to lose energy. Every massive object that is climbing out of a gravitational potential well loses energy. Now in the case of a photon, it cannot lose energy by slowing down. It just can't happen. Photons can only exist at the speed of light. How do photons lose energy? They lose energy by changing their wavelength. Longer wavelength, lower energy. So they have either longer wavelengths or they have lower frequencies. So we expect what is now referred to as gravitational reddening. Gravity itself takes some of the energy out of the photon and makes it turn red. Similar, but not the same thing, similar in its results to the Doppler effect. You know, there's Doppler redshift for light if the star is moving away from the observer, and we have gravitational reddening as well. So I'd like to talk a little bit about that. As you recall, potential energy, potential energy, if you're in a gravitational well, you remember from your physics 4 class, it was simply G m over r. G is the universal gravitational constant. I'm using capital M to be the mass of the star, little m to be the mass effect of a photon, and r to be your distance away from the center of that object. You're in this physics 4, this is the gravitational potential well. Well, what we're going to talk about right now is the energy of the photon that you detect. So I'm going to call this E prime. Imagine you're some distance away from the star and you're actually detecting the photon. It has energy E prime. It must equal the energy that it started with minus the energy lost to gravity. Wouldn't it be nice if we could figure out what the mass effect of the photon was? Well, to do that, it's actually pretty easy because, as you recall, any photon has a momentum P equals E over C. Remember, E equals PC from massless particle arguments. So that's pretty easy. We can just put in for mass mv equals E over c. M, of course, is going to be E over c squared because the velocity of a photon is the speed of light. So we can just insert that then right here. So now we have that E prime equals E minus G M over R. And lo and behold, we have an energy in both places, so we have E times 1 minus G M over R C squared. And replacing that then, we can just, well, let me do this first. E prime over E is going to equal 1 minus G R C squared. And of course now I can replace that with E equals H nu. So this is just going to be nu prime over nu 1 minus, same old thing here. But let's do this. Let me move this over here and that over here. So I end up with G M R C squared equals 1 minus nu prime over nu. That's nice. But let me rewrite this, if you will, nu minus nu prime over nu, like that. Or perhaps more conventionally, we could write it as, oh, no, we'll write it just like this. In fact, what I wanted to say was, what if we have a situation, where there's so much gravity, nu prime is 0. What does that imply to you? Let me ask that differently. What common scientific curiosity do you think we're about to talk about?
Black holes.
Black holes, yes. What if we get into a situation where the energy required for a photon to leave the surface is greater than the energy the photon has? You have a black hole. Well, in that case, of course, then you get that G M over R C squared equals 1. Perfect. That's really nice. We can now calculate R. R, at what radius will this thing become a black hole, is simply G M over C squared. And there is a problem here. There's an assumption built in, which I'm not going to fix right now. I'm just going to suggest to you that when we fix the problem, that is when general relativity is taken into account, actually we have to argue that Gm over R C squared actually equals 1/2, not 1. Can anybody see? There's a logical reason. You can see it if you stare at these equations for just a moment. You can see why it is, what assumption I made over here, or what little point I glossed over. I didn't really make an assumption, I just glossed over a point that led to 1, and really this number should be small. In fact, it's even logical that it should be 1/2. Does anybody know what it is? I see it right now, finally. I see where I put it. We put in, for the mass of the photon, the initial mass of the photon. As it's leaving the star and its frequency decreases, its mass decreases. So this is not a constant number, this is a decreasing number, which essentially starts at this and ends at 0. So really, the number we should put here is 1/2 of this number. because the mass changes, and when I put this in, I'm assuming a constant mass. So, without fixing it, you really have to put an integral in there, and we don't want to do that. Let's just take, for example, it needs to be this. Hence, therefore, we can write that r, the radius at which the photon loses all of its energy, will simply be gm times 2 over c squared. 2gm over c squared. That's what's called the Schwarzschild radius of a black hole. One of the things I wanted to do today, but we don't have time, let's calculate the Schwarzschild radius of the sun. Do that as just a fun project on the side. But what I want to do is I want to get into today's measurement. So I wanted to mention this and then talk about the hydrogen spectrum. So, for the fun of it, find out what the Schwarzschild radius would be for the sun. In other words, how small would the sun have to be so that light could not escape from it? Use the solar mass, and that's all you have to put in there. Solar mass, universal gravitational constant, speed of light squared. Easy calculation to do. I believe you will find it to be a remarkably small object. The sun would have to be a remarkably small object. Let's leave it at that. Talk more about this at some other day. Now what I'd like to do is talk about today's principal measurement. What we want to do is make sure everybody gets a measurement done today. A simple one that you've already done, but with a special technique of it.
What was the E formula?
That's the energy of the photon at some distance away from the center of the star, after it's lost some energy with gravitational redshift. Here's what we're going to do today, folks. The hydrogen spectrum is going to be investigated. I'd like you to look at hydrogen and measure the hydrogen spectrum. It's a very simple project, except for one thing. Hydrogen being such a sneaky little molecule, if you let these tubes get warm at all, the hydrogen sneaks out. So, what I'm going to ask you to do, when you're going to do your experiment, set up using a mercury source. So, when you're going to set up and get everything aligned, you can turn the mercury source on and do like you did before. Everything's working along just fine. Now you've got everything set, you're ready to do the hydrogen. So, get a hydrogen bulb. Get a hydrogen bulb. Put it in the system. Turn it on. Find a measurement that you want. As soon as you get on that measurement, turn it off. Now you can make your reading and do your recording. Everything is fine. Switch it on again. Go to the next color. Switch it off. All I want you to do is make sure not to get that hydrogen bulb hot or even warm if you can avoid it. That's the only trick you're going to have to do, is just when you're using the hydrogen, turn it on, find a color, turn it off. Make your reading, make your recording, switch it on, move it again, and switch it off. Okay, that's the only difference.
How do you know if it does escape?
The light will go out.
Ah, okay, just checking.
The little box will hum and there'll be no light coming out of the tube. So I've got some mercuries up here and I've got some hydrogens. It looks like I'm going to have to go find some more mercuries. I think what I'd like to do, rather than explain any of the calculation, I'm going to let you work from now. I'll give you an hour. At 10 minutes to 9, I'm going to come back and turn the room lights back on and talk just a little bit about the calculation. And then Wednesday, we're going to talk about the theory. So at 10 minutes to 9 or so, we'll talk about the calculation, and after that, on Wednesday, the theory. So grab some of these balls up here, I'll find some more.
This is nice, I think.
energy, what do we have? KE equals m naught v squared over 1 minus beta squared minus m naught times this integral, so it should be this term right here. What's that? Something strange is happening. Excuse me for just a moment. In-class problem, so we just demonstrated that we have the kinetic energy is equal to minus m naught c squared times the root of 1 minus beta squared plus m naught c squared, like that. And oh, I see. Haven't finished this over here, have I? So let me see what I get here. I seem to have skipped a page in my notes. I don't know why I did that, but I seem to. My next claim is that it becomes, oh, I think I see it. I think I see it. If we factor out, let me see, m naught v squared, 1 minus beta squared, plus m naught c squared root of 1 plus beta squared minus m naught c squared, like this. And then we try to combine, we endeavor to combine these two terms. We can do that by multiplying this term by 1 minus beta squared over 1 minus beta squared, both of them on the square root. So let's take a moment and look at this term here, m naught c squared root of 1 minus beta squared times 1 minus beta squared over 1 minus beta squared. That will put it over the same denominator. If I do this, what happens? I end up with m naught c squared times 1 minus v squared over c squared divided by root of 1 minus beta squared. And this is the missing page of notes. So watch my algebra closely. And when I multiply that thing out, let's see, what do I get? I get on top, we're now just concentrating just on this term right here. So, what do I get? M naught c squared root of 1 minus beta squared becomes m naught c squared minus m naught v squared over 1 minus beta squared under the square root. Now insert that right here. So kinetic energy becomes m naught v squared 1 minus beta squared plus this term plus this term, m naught c squared root of 1 minus beta squared minus m naught v squared over 1 minus beta squared minus this term, which is minus m naught c squared. Now let's check and see if I did that correctly. What I just did was to put this term over that denominator using this. That done, I get m naught c squared times 1 minus beta squared over that denominator. Then I stuck that right back in here, so I've got this term at the beginning. Let me just check. I've got this term at the beginning, I've got this term at the end, and I've got this thing in the middle. Looks good to me. Does it look good to you? Great, I'm happy, because, of course, we see m naught v squared over 1 minus beta. We see minus m naught v squared over 1. It's gone. Great, fantastic. We did what we wanted to do. We got rid of this ugly, nasty thing. And so what do we have left? We have left that kinetic energy. Is it? How come you're not excited? Isn't this fun? Aren't we having fun? Is equal to m naught c squared over 1 minus beta squared square root minus m naught c squared. But of course, we recognize this creature, use a different color, blue. We recognize this creature right here as simply m, not m naught, but m. So, kinetic energy is equal to mc squared minus m naught c squared. That's how Einstein made the discovery, ladies and gentlemen. E equals mc squared. Or a better way of writing it, I like it better anyway, is to write that mc squared is equal to m naught c squared plus kinetic energy. And then we realize that this term, mc squared, is total energy. Energy total equals mc squared. Something we call rest energy is equal to m naught c squared. So the total energy of a particle is its rest mass energy plus its kinetic energy. E equals mc squared. Mass and energy are equivalent to each other. And the way we describe that is to call this thing the rest energy. So an object of mass m naught sitting stationary possesses energy. I like to think of it as a form of potential energy. Rest mass energy is a form of potential energy. So on my paper I wrote E equals mc squared exclamation point. So the old-fashioned conservation of mass and conservation of energies, which I think is a law that they actually still teach in chemistry, don't they?
Yeah.
Yes. It ain't so. There is not two separate laws. It's conservation of mass energy. Mass and energy are two different manifestations of the same thing. In a reaction of any kind, chemical reaction or any kind, the only thing that remains constant is the total of mass plus energy. You don't have a conservation of mass and a conservation of energy. It's a single law.
We could transfer some mass to energy and/or energy of mass.
Absolutely. Absolutely, and this was an amazing discovery and I think I might be aware, I might be cognizant of that dubious look some of you are giving me.
Under what conditions would that happen?
First off, yes, that's a key question he asks right there. And first off, you have to get a feeling for what you're talking about. Let me give you an example. 1 kilogram of mass, which is just a little bit less than the mass of your book, how much energy is there? Well, it's really easy. How much rest mass energy is there? It's simply m naught c squared, 1 kg of mass times 3 times 10 to the 8 meters per second squared is 9 times 10 to the 16 joules. Sounds big, doesn't it? It is big. I thought of an interesting way of sort of getting an idea of how big this amount of energy is. And I asked myself this question. This amount of energy, how far above the Earth's surface will it lift a given mass? I thought to myself, that might be an interesting way of determining it. So I thought, well, let's take an unknown mass to the moon. Let's find out how much work is required to move an unknown mass to the moon and then calculate how much mass this amount of energy would move to the moon. So how would you do that? You got to think back, of course, to your Physics 4 days. But if you were back at Physics 4 and you wanted to lift a mass from the surface of the Earth to the moon's orbit, as far out as the moon, what would you do?
Force times distance.
So work equals, of course, the integral of F dot ds. And for us, we're going to assume we got a rocket, so the force is parallel to the displacement, so we don't have to worry about the dot product. What would you put in for force?
Force of gravity.
Yes. The integral of G, capital M with a circle and an X in it, small m over R squared dr. Now, S has become R because I'm measuring radii. So there's the force of gravity. Since you're moving to the moon, the force of gravity is not constant. We only use F equals mg when you're sticking close to the surface of the Earth. So what did we put in here? G, of course, is the universal gravitational constant. It is a constant. This m is what? When it has a circle with an X in it, what is it? That's the Earth's mass. This is the radius to which we are moving. What is this little mass? That's the unknown mass that we are lifting. That's the one that we're looking for. And of course, so we can pull all of this stuff out front. Now go ahead, your question.
Technically, you're missing a part,
Technically, I'm missing a part, what?
because the moon has mass too.
Okay, technically we're missing a part. He's talking about the fact that when you get really close to the moon is going to attract a little bit, but we're just making an estimate. We're not being technical right now. But you are correct, absolutely. If we were, if we were JPL, we'd take that into account. You can do that when you transfer to Caltech. And that's your ambition, every one of you, right, to go to Caltech. Second best university in the world. So, what we have then is G, M, integral from 0 to R. Here's another technical point, if you notice it. I'm not going to say it right off. dr over R squared. Okay? That's all we have to do. We assume that we do the appropriate amount of work. Let us assume that we do this amount of work, so we've got a number for W. We've got a number for all of this. So what we have then is that work divided by G, M, must equal the integral dr over R squared, like this. And that's the radius of the moon's orbit. So when we're done, really, the unknown mass goes here and the integral goes down there. So the unknown mass that we are lifting is equal to the work that we do divided by the universal gravitational constant, the mass of the Earth, and the integral from 0 to the radius of the moon's orbit of dr over R squared, which of course is simple. So we've got everything we need, except, of course, putting in the numbers with the correct units. When I was done with this calculation, and I challenge you to finish the actual calculation, I don't want to look up all the numbers right now, but I got about 1 million tons. What I just said, ladies and gentlemen, is the amount of energy locked up in your book as mass energy is enough energy to lift 1 million tons to the moon. That's a hell of a lot of energy, isn't it? That's true. That's what mass energy is all about. Now I can get around to your original point, which was a good point. And basically, I think if I understood what you were saying, basically it was like, oh yeah, how come we never saw this before in chemistry? When you use conservation of mass in chemistry and you use conservation of energy in chemistry, it works. Why? It's because the kind of reactions that you're doing aren't anything like this sort of energy, are they? They're so puny, you never notice the missing mass. I think we've got another example problem before I go on here. Yes, look at this. 1 kilogram of dynamite liberates about 5.4 times 10 to the 6 joules of energy. It does it by losing mass. When you detonate a kilogram of dynamite, it converts some of its mass into energy. Let's figure out how much mass is converted into energy, because that's a pretty energetic chemical reaction, isn't it? A kilogram of dynamite is a pretty energetic chemical reaction. So, let's put on the board here what's going on. That is 1 kg of dynamite. .4 times 10 to the 6 joules of energy are released. So we ask, m naught c squared equals 5.4 10 to the 6 joules. How much mass disappeared in this reaction? So m naught is going to be 5.4 10 to the 6, what are the units on joules? kg, meters squared per second squared, divided by c squared, which is 9, 10 to the 16 meters squared per second squared. Nicely, the units work out beautifully. And of course, we have 9 into 5.4, which is 0.6. 10 to the 16 downstairs, 10 to the 6 upstairs, so that's times 10 to the minus 10 kgs, or about 6 times 10 to the minus 11 kgs. I defy you to measure that after the explosion. Detonate a kilogram of dynamite and then go find that you have this much less dynamite particles left. Or, the way a lot of people say it is, this amount of mass is very hard to notice, whereas the energy release is hard to ignore. Yes?
So, is this implying that all the energy released is because we're doing mass to energy?
Yes. Did you hear what he said? He said, does this imply that all energy release is a conversion of mass into energy? And the answer is yes. It's just that the kinds of energy releases we are used to represent such a puny loss of mass that we never noticed it before.
So it always is?
It always is. Anytime you have any energy release, it was at the expense of mass someplace. Just don't forget that we deal with puny amounts of energy. This is considered a puny amount of energy compared to that one over there, huh?
So that's
Correct.
not just like nuclear energy, that's any
Nuclear energies are about 1,000,000 times more energetic. A nuclear reaction is about 1,000,000 times more energetic than a chemical reaction. Nuclear nuclear, about 1 million times more energetic than chemical. And that's why when you do nuclear reactions, you actually do notice mass missing. You do nuclear reactions, and you can actually measure the missing mass, but not in chemical reactions. It's so small, it's almost beyond our ability to do experimentation. Okay, now I have another very interesting question for you, and that is what happens when v is small. We've been thinking about things relativistically. We always think about things where velocities aren't high. What happens when the velocity is small? This is kind of an interesting consequence, and I want to spend some time discussing it after we have noted the consequences. What if v is small? What happens then? Well, it's kind of interesting. You already know that kinetic energy, relativistically speaking, is total energy, mc squared, minus rest energy, m naught c squared. Which, of course, could be written as m naught c squared times gamma minus 1. Let's fill in for gamma a little bit at least. M naught c squared, 1 over 1 minus beta squared under the square root minus 1. And the reason that we do that is because when v is small, of course, beta is much, much less than 1. It is also small. So we're talking about small, shall we call them ordinary velocities, velocities of spacecraft and things like that, maybe asteroids and things like that. What goes on? Well, the neat thing is we can evaluate this quite nicely by simply doing an expansion. All we have to do is expand this term. That is 1 minus beta squared to the minus 1/2 power. And as you recall, the binomial expansion, 1 minus x to the n is equal to, well, 1 plus nx plus, and it never ends. There's a long, long set of terms. But if x is small, the next term is x squared, which is trivial. So we're going to approximate it by keeping just 1 plus nx. The rest of it is real but trivial, because every subsequent term is a higher power on x, and we've already argued that x is small. That is beta. So, I have that right. Oops, I don't have that right. Ladies and gentlemen, I don't have that right. Please fix that on your notes. So, I can say then that the above expression, just ditto marks if you will, is equal to 1 plus n x and I get a double negative. I get a negative because that's a negative 1/2 for n, and I get a negative because plus negative beta squared. So this simply becomes then 1 plus beta squared is our, what do we do? See, I told you. Plus 1/2 beta squared. And we can simply insert that right here. So we get then that the kinetic energy is equal to m naught c squared times this creature, which is 1 plus 1/2 beta squared minus 1 1 minus 1, that's nice. So we end up with, then our new kinetic energy, Ke, equals m naught c squared times 1/2, write that a little nicer, times 1/2 v squared over c squared. Lo and behold, we get 1/2 m naught v squared. Have you ever seen that before? Never. What a surprise. I've never seen that before. It is not a coincidence that the relativistic formula reduces to the classical formula when you're dealing in classical velocities. It's not a coincidence. As you know, for hundreds of years after Newton's time, people tested classical formulas and they worked beautifully. You tested classical formulas in your Physics 4 and they worked beautifully. A requirement on this new study of relativity, a requirement is no matter what your conclusion is in relativity, it must reduce to a classical conclusion under these conditions. If beta is very small, implying if velocities are quite small, you better get classical results. Why? Because we've been getting those in experiments forever. We know that the classical situation works beautifully in classical experiments. So, one of the tests you give to every new relativity idea, one of the tests you give it is, okay, this is a conclusion of what's happening in a relativistic situation. What happens if we slow everything down to classical speeds? You better get the classical result, just like this did. Okay? So one of the things I like to do, I like to think of it like this. Here's classical mechanics, just call it CM, classical mechanics, or Newtonian mechanics. Relativistic mechanics is like this. Relativistic mechanics must completely encompass classical mechanics and then give you further solutions beyond what classical can do. Classical can only handle low velocity. Relativity should be able to handle both. If relativity is correct, then it must be able to handle high velocities and low velocities. So, relativistic mechanics, RM, must completely encompass classical mechanics. That's a requirement. Pretty neat though, huh?
Yeah.
I can see how excited you all are. Let's go out and have a carbonated beverage.
Okay.
Awesome.
All right. So does that takes care of this page. Unfortunately, it is. You know what? Quantum mechanics would go sort of like this. Look. There's quantum mechanics.
That's fine.
Quantum mechanics does seem to do a great job of taking into account classical. Both quantum mechanics encompass classical, but they don't talk to each other. Quantum does not talk to relativity, relativity does not talk to quantum, but they both talk to classical mechanics. Isn't it funny? It's a little bit like the zeroth law of thermodynamics. That is, remember we said that if object A is in thermodynamic equilibrium with object B, and object B is in thermodynamic equilibrium with object C, then A is in equilibrium with C, right?
Yeah.
Well, here we've got A and B, we've got A and C, but we haven't yet got C and A together. C and B together. We haven't got those other two together anyway. It's like we haven't finished the zeroth law of thermodynamics when it comes to the different mechanics. Now, you had a question, Christina?
I was going to say, why not?
Because you haven't finished yet. You must finish your PhD and then you can do it. I guarantee you, when you have finished this, you will get a Nobel Prize. And life will be wonderful. So much better than winning the lottery. Everybody goes and plays the lottery, right? Chump change. Chump change compared to winning the Nobel Prize. The nice thing is, the lottery is pure random, but the Nobel Prize has to do with how much you work. So you can win a Nobel Prize. You can set out to do it and win. All I ask is when you step up to the microphone to receive your prize, you say, I owe it all to Dorio. Why not? We're not done yet, that's why not. Okay, I got a new topic, if we're ready to go for the new topic. One last page. 2 pages to go. We only got 2 pages to go, we got almost enough time to do it. All right, any questions about what we've done so far before we get on to the next bit here? The next bit's really neat too, you're gonna like this, is fun. Yes? Because what I'm talking about is the dynamite's just sitting there, and then some of that rest mass is, a small amount of that rest mass is converted. So that's why I chose it.
But only the why you didn't add the taking kinetic energy to one side or the other. You said the rest mass was equal to the square.
Because you need this rest mass here,
No, above the first line.
above it, up here.
Yes.
Because what I'm saying is how much energy is sitting there in that book right now. That book is sitting there stationary. Okay? Subtle, but the type of question you need to ask yourself every single time you do this. Which M do I put in and why? So, subtle question he asked, but an important one for you to ask of yourself each time. All right, I want to go on now to the new and final topic. Final topic? No, it's not. The new and the second to the final topic today. That is, can massless particles exist? You said yes. How do you know? Because somebody told you? Nah, we're physicists. We're going to check it out. We don't care what anybody else says, even Einstein. We're going to check it out. Can massless particles exist? Maybe. Let's check it out. Here's how we do it. Let's start by describing the energy of a massless particle. So the energy of a massless particle, of course, is mc squared. M naught c squared over 1 minus v squared over c squared under the square root. And the momentum of a particle, P, the momentum of a particle is, of course, mv, M naught v, over 1 minus v squared over c squared. Okay, there's the mass and, there's the energy and the momentum of a particle, Of course, you notice that if m naught is 0, if m naught equals 0 and v is less than c, then E equals P equals 0. Right? If m naught is 0 and v is less than c, then this is some real number, and that's 0. Likewise. Well, a particle with no energy and no momentum is no particle at all. But put a big but on the board. But if m naught equals 0 and v equals c, then E equals 0 over 0 and P equals 0 over 0. And what do the mathematicians, careful, what word do the mathematicians use? Indeterminate. That says E could be real, and P could be some real finite value. Hence, therefore, we conclude that if massless particles exist, they can only exist at the speed of light. If they exist below the speed of light, there's no energy, no momentum, you really don't have a particle. If they exist at the speed of light, then there's a chance that you could have an energy and a momentum. And by the way, a subtle little point for your future lectures. You see how I did this? E equals P equals 0. Do you know why I did not write E equals P equals 0 over 0? I did not write this. I'm going to put a big X through it. For a very specific reason. That's correct. They might not be the same. They are both indeterminate, but they are probably different. They're indeterminate, but they're probably different. That's why. Yes, good point. Where am I? Ah. So, we have concluded that there's no way to get rid of them. We haven't concluded that we haven't proven that massless particles exist, but we have found no obvious way of saying they do not exist. So, if this, then this, if that, then that, so maybe, that's what I wrote on my paper. So maybe. If and only if, so you write that down, don't you? If and only if I, F, B equals C. That's the only way massless particles can exist at the speed of light. I suspect you know which particle I'm talking about, but I haven't given it a name, and I shouldn't give it a name for about 2 more lectures, but I suspect you know which particle I'm talking about. Which particle am I talking about?
Photon.
That's correct, the photon. And the photon, all I can say to you is that when photons are cruising around, they exist. And if you stop them, they don't exist anymore. You slow a photon down below the speed of light and they don't exist anymore. But anyway, I'm not supposed to say that, so you know that. Now, here's something else.